Certainly you will remember this contraption. A solid cylinder pivoted from a bearing, a mass M, force of 9 newtons acting on it. Diameter is 0.12 meters, so 0.06 meters is the radius. And so this force is going to be applied for 2 meters. And the question is, amongst other things, what's the speed after 2 meters of line is pulled? And that we did with energy earlier. We're going to do it dynamically now and also answer the question about the angular acceleration and the linear acceleration of the cable in this case. Angular acceleration of the cylinder. All right, so let's start with the free body force diagram. Now with free body force diagrams, you're used to putting all the forces acting on the body and modeling that as a point. Well, now we're not going to model it as a point. We're going to model it as an extended rotating entity. So we put a circle. It's kind of like the cross section of the cylinder here. And it's really important to do that because we need to place the forces at the appropriate places. So mg acts straight down, and you can think of it acting from the center of mass. So that's a logical place to put it. Now the string or the cable is a force acting on the cylinder, but it acts on the edge. That's important to recognize that there's a radius of 0.06 meters across it from the point of rotation, which is here. So that's going to obviously produce a torque on this thing. Now we also have a normal force. The normal force is the bearing shoving back up onto the cylinder. Now that's a little confusing to you. I think it should be straight up. Well, it would be straight up if it was just mg, but because we're pulling this way, for the cylinder not to translationally accelerate, it better have a force on it that's equal and opposite to this applied force, and that's also provided by this normal force. So if you add up all three of these vectors, if you take this and add it here and then add this one, tail to tip on there, you'll have a closed triangle. There's no translational acceleration. Okay, so that is a new way of constructing a free body force diagram. And the sense of positive rotation is going to be clockwise here, just to show that anything going in the other direction to be negative. And then it's important to recognize that the normal force and mg exert no torque. Now, why do they exert no torque? You might already anticipate the answer. It's rotating from this point here. So if there's a normal force acting through that point, there's no moment arm across which to apply a torque. In other words, any force acting where the line of action goes through the axis of rotation can't produce a torque because there's no R in the R cross F. Right? So hopefully that makes sense. The only force acting on this that can produce a torque is the applied. So if it goes through the axis of rotation, the force does not produce any torque. Now, the torque is FL in this case, and the L is just simply the radius. Okay, so that's the essential L. So 9 times 0.06, 0.54 Newton meters. The angular acceleration, we just learned about the relationship between angular acceleration, torque, and moment of inertia. Torque is I alpha. So alpha is torque over I. And so FL over 1/2 mr squared. Remember 1/2 mr squared for a solid disk or a cylinder. 2FL over mr squared, 2 times 9 times 0.06 over 50 times 0.06 squared, 6 radians per second squared. So there's the angular acceleration. Now the linear acceleration is just, the acceleration of the string or cable here, which is the acceleration of the edge of the cylinder, is the A tangential, and that's R alpha. So that's 0.06 times 6, 0.36 meters per second squared. And V at 2 meters, we did it with energy earlier. Now, essentially we're at the point of almost doing the same thing. We know the acceleration, and it's a constant acceleration. So V is square root of 2AD, constant acceleration expression, 1.2 meters per second squared. The same results we got with our consideration of energy. So this was an important slide, an example to show you the method of solving for a torque and angular acceleration problem, how to do the free body force diagram, etc. You will also recall this little system that we analyzed with energy. We didn't analyze it with the growling dog in the background, the ferocious Sheltie that roams the Brust residence here. But nevertheless, we have a cylinder, mass large M, spinning around, small mass M attached to it, height h. And we're going to find, using dynamics, the acceleration of the mass and the tension in the string. Different quantities than we've found before. Before we just used energy and looked at the velocity or speed at which it struck the floor. All right, well, we need to do free body force diagrams. And we're going to do one for both of the applicable objects. So we have little m and we have mg and tension. Those are in tension with each other. And who wins but mg, of course. So the sum of the forces in the y, mg minus t, is ma. That's one of our two expressions that we'll use to solve this problem. Now let's do a free body for the cylinder. And the direction of positive rotation is counterclockwise in this case. And big mg points straight down. We got the radius. Through the radius we have a tension. I hope you realize this tension is not mg. You better realize that by now. And then we have a normal force acting vertically upward. Of course, the normal force has to overcome the weight and overcome the tension. So it's the addition of these two. Otherwise, the whole system would accelerate vertically, which of course it doesn't. So sum of torques is, well, it's the whole amount of torque acting on this is R times T. They're perpendicular to each other, and that's I alpha. So I is 1/2 mr squared times alpha. We can expand this to say 1/2 mr times R alpha. Well, why do I want R alpha in here? Because R alpha is atangential. That's why. So since atangential is R alpha, we have that R times T equals 1/2 mr atangential. Radius, the radii go away, and we have T is equal to 1/2 ma. So there's an expression for our tension. That's kind of nice because we really don't want, well, we do want tension actually, but to get the acceleration, we don't want it in there. So let's combine these two things, these two equations, and solve the problem. So here's our two terms, two equations that we got from our free body diagrams. Let's add these together, and when we add them together, you'll notice that these t's will cancel on the left side. So we have mg equals ma plus 1/2 ma. So let's factor out the a, and m plus 1/2 m. So a is equal to mg over m plus 1/2 m. All right. Well, you know, I generally don't like a variable sitting there twice, so let's multiply by 1 over m over 1 over m and get rid of that little m like such. Now tension is 1/2 ma, just bringing this down. So let's go ahead and take 1/2 of big M times A. Well, I'm going to go ahead and use this expression for a reason. So here it is. And when we multiply that, we get little m big M G over 2m plus big M. This can also be written as, if you take 1 over little m times 1 over big M over 1 over little m times 1 over big M, you get this reduced down to a single big M and little m. That's nice. That would be my preferred way in general. But let me violate that just for a little bit for a reason. So here's the tension. And it's 1/2 m A, where A is G over 1 plus big M over 2m. So that's what we have. And this enables us to see what happens when big M is much greater than little m. Well, if big M is much greater than little m, then it dominates. It's like a huge rotational inertia. Therefore, the tension should approximate mg, and in fact it does. If this is real big, this diminishes to almost nothing, so we get T as mg. The acceleration is very small. When m is equal to 0, well then this goes to infinity and the tension goes to 0, which means the acceleration is just g, as we would expect. So now what's the speed when it hits the floor? Well, we have a constant acceleration, so v is rad 2ah, which is, take the square root of 2a times h. Well, here's a, so we have the g over 1 plus m over 2m. There it is. And plus the 2h, which is exactly what we had for the result for speed when we solved it using energy. Very satisfying indeed. In this example, we're going to have a couple of masses on a frictionless table. Well, one mass on a frictionless table, the other hanging over a pulley. And the pulley has mass big M. The other two masses are M1 and M2. And there is a tension here and here. And I hope you realize that these tensions are different because we have a non-zero mass here. If you put a regular mass between two strings, those tensions are somewhat, to some degree, isolated from each other. Not totally isolated, but the mass that's in between them alters the specific tension of each one. So we have an acceleration to the right in this direction, and of course down for M2. Let's find the acceleration of the system, the angular acceleration of the pulley, T1 and T2. We're going to need three free body force diagrams, one for each of the masses, M1, M, and M2. So let's go ahead and do that. So for M1, we have M1G and the normal, and T1, which accelerates it. There's no resultant force vertically, so sum of Fx equals M1A, thus T1 equals M1A. So there's one equation. Now let's do an equation for M2. M2G, T2. Of course, M2G is bigger than T2. And I hope you realize, though, that this tension, regardless of how I show the relative sizes here, this tension accelerates not only the pulley, but also this mass. So therefore, it must be larger than T1. Okay. Well, the sum of the forces in the y then is M2A. So we have M2G minus tension, T2 is M2A. So there's our second equation. And now we have yet a third equation. Cap M, sense of positive rotation here. Big MG, T1, and also we have T2 acting in this way. We have the radii as such. And the normal force. What direction is the normal force? Well, for this thing to stay put, we have this real force, and this real force. So we better shove up this way in order for the whole thing not to accelerate, and that's exactly what happens. I'm not saying they're to scale. All these vector forces would add to 0. But now, with this third free body, we have sum of torques is I alpha. Notice we have two torques acting in opposition to each other. So let's take that into consideration and solve the rest of the problem. So sum of torques is I alpha. The sum of the torques is T2R minus T1R. So they are opposing each other. Both of the tension forces are working through perpendicular radius r, nevertheless. All right, so that is equal to I alpha. I is mr squared. If you recall, that's the moment of inertia for a pulley in this case, with all the mass concentrated on the outer edge, connected by massless spokes. So these 1r goes away in this. Keep in mind that the normal and the mg don't apply any torque because it goes through the line of action is through the axis of rotation. So alpha is a over r, or a is equal to alpha r. So we have T2 minus T1 is m r alpha, but MR alpha is just MA. So we have three simultaneous equations, T1, M1A, M2G minus T2 is M2A, and our third expression, T2 minus T1 is MA. Let's add these. Now if we add these three simultaneous equations, very happily, T1 minus T2 plus T2 minus T1 all disappears. So on the left side we just have M2G, and then on the right side we have M1A, M2A, and big MA. Everything has A in it, so we can factor out the A and have M1 plus M2 plus M multiplied by. So we solve for the acceleration, M2G over M1 plus M2 plus M. Now, before I scoot on to the next thing, it's very interesting to note, you're not surprised that this is the impetus, M2G, to accelerate the whole system, and it's divided by the sum of the masses. But wait a minute, look at big M. Big M has equal weighting as a translational mass, doesn't it? Like if we had this block on the table, it'd be the same thing. And the reason is because all the mass is concentrated on the outer edge for that wheel, for that pulley. And so all the mass is accelerated, yes, rotationally, but you can think of it as linearly as well, because the resultant speed of the mass at the end, all the particles of mass, are the speed of the string that goes over it. So it's as though you're linearly accelerating all the mass. Of course, if it was a disk, it would be 1/2 here. I'm trying to write 1/2, not being too effective. But that's the way that works. So if it's a maximally maximum rotational inertia for an object has the same effect as translational inertia. Hopefully that makes sense. So the angular acceleration is just a over r, so we have this divided by r. Now T1 is ma, so m1 times a, which is all the rest. What about T2? Looking at this, we can solve for T2. We get m2g minus a, which is m2g. G factors out. There's the 1, and the a already has g in it, so that works. M2 over M1 is plus M2 plus M. This is M2G times, well, to get rid of this 1, I'm going to say M1 plus M2 plus M over M1 plus M2 plus M minus M2 over all that. Well, that's nice because this M2 goes away and we can express it fairly succinctly. There is our expression. And we have solved for all the various variables that were in question.